So I wanted to make a video on gradient descent to just show how this is typically implemented inside of production software like sklearn, pytorch, tensorflow, things like that. A lot of times when gradient descent is taught, it's taught analytically. And so you see examples like this where somebody is, let's say, using gradient descent to find the equation of a line of best fit, right? And they will take some loss function that we want to optimize, we want to find the minimum of, and then they'll go through and they'll actually derive by hand the derivative of that cost function so that we know in which direction we have to push the parameters of our model to minimize the error. In reality, though, this is not how this is done in production software. And so I wanted to make a video about this to show the reality is it's actually much easier than this. So let's start by just taking the gradient of a line, which is easy to do because gradients of lines are constant. They're the same everywhere along the line, no matter where you look. And so we think about rates of change or your gradient as how much the output of your function changes with respect to how much the inputs of your function change. So if for a very small change in x, the output of our function f of x changes a lot, then you have a really steep rate of change. Your rate of change is very high, your gradient is large. The opposite is also true. If for a large change in x, the value of the output of your function changes very little, then your gradient is very small, right? Your function is not changing very quickly. So for a line, you can just pick any 2 points along the line, or sorry, any 2 inputs, x1 or x2, along the line, and you can calculate the gradient that way. However, this gets a little bit more complicated when you get into curves because, how fast is your function changing at any point for any input x? Like, how do you think about that? So this here is the standard equation for your derivative that you would have learned in pre-calc or calculus, anytime. And the important thing to understand here is that it's kind of conceptually no different from what we did to calculate the gradient of a line. So let's just pick some random input to our function x. And then let's pick another one in front of it, x plus h. Okay? Now, if we were to draw a line between these 2 points, the slope or the gradient of that line would be given by f of x plus h minus f of x, how much the output of our function changed, divided by h, which is how much we changed the inputs to our function. Okay, and that is exactly what we have here in our equation for our derivative. Now notice if we just strip away all the annotations here and just draw the line kind of connecting these 2 points, as h gets smaller and smaller, the line between those 2 points starts to approach the tangent line to our function at our input x. And so as h gets smaller and smaller and smaller, your approximation of the instantaneous rate of change gets more and more accurate. And so this is how we actually think about derivatives or gradients is what we'll refer to them as here, and how they're useful. And this is the way in which we're going to differentiate cost functions. It turns out to be a lot easier to do it this way. Okay, so now let's actually talk about how this gets used for gradient descent. Let's imagine that we're trying to find the line of best fit through some data, and we're only concerned with finding the best slope of the line that minimizes our cost function. Okay, so in this case, our cost function is a function only of the slope of the line, where we'll ignore the intercept. So we have m here and then c of m. For some initial guess, m naught, of our slope, we want to understand, okay, do we need to increase the value of our slope or decrease the value of our slope to minimize our cost function c of m? We don't even need to know what our cost function is in order to do this. We can just use the formula that we showed previously, right? We can just do this thing. The question is, there's a limit here, right? As h approaches 0 of this quantity. So how do we actually do that? The answer is just pick some really small value for h. Okay, so our gradient of C of m at m naught, okay, is given by this. We just plug in, here I use 0.001 for h, but in reality, you could make this even smaller if you wanted, and your approximation would get better and better and better until you get into like rounding point error, okay? So this is how you do this. We have just successfully calculated the gradient of our function at this point. We didn't have to know what the function was, we just had to be able to evaluate it. Now, the standard procedure with gradient descent is if we think about, okay, if the gradient of our function is increasing at m naught, which direction do we need to move? Do we need to move to the left or to the right? Well, if we keep moving to the right, C of m increases, so we need to move to the left. And in general, we need to move in the direction opposite of our gradient in order to minimize our cost. So the next value of our slope that we're going to test is equal to our current value minus the gradient at that point. Now, sometimes your gradients get really large, which means that we would be taking really large step sizes, and so you might step over the actual minimum of our cost function C of m. So typically we scale this by some learning rate, which is a hyperparameter. You choose it. In a lot of cases, 0.05 is sufficient, sometimes 0.005, sometimes more if you're dealing with a particularly unruly neural network. But this is the general formulation for how to take steps using gradient descent. You take your current point, subtract from it the gradient at that point times your learning rate. And we can do this over and over and over again until we converge to the minimum of our function. And if I just kind of render the function here, you can see we're descending this thing here perfectly. So this is the way that autograd engines, programs that actually implement gradient descent, this is the way that they work. They don't concern themselves with actually explicitly calculating the derivative of your cost function with power rule, chain rule, whatever. They just evaluate your function between 2 points very close together to one another to approximate the gradient, and then they use that to perform this gradient descent procedure. Okay, so let's just go through quickly how this kind of works in code. All right, so what we'll do is we'll do linear regression with gradient descent, but using the technique that we just discussed. Right, so we'll import some packages, define a helper function that takes in our input array x and returns the predictions of our line given a slope m and an intercept b. This just keeps me from having to write mx plus b all over my code, makes things nice. Next, we want to generate a synthetic data set here. I could have pulled an example data set from sklearn to do this, but keeping everything two-dimensional with synthetic data is nice. So here's kind of the data set that we'll work from. We have our inputs x and then our target y that we're trying to predict with our line. Now, it's important to note here that in order to do this, basically I kind of worked backwards. So I started with a actual slope and intercept of a line and then added random noise to that to get this distribution. So when we're done with gradient descent, we know that we should be at about 5 and about 13 for our slope and intercept respectively. It's not going to be exactly that, right, because we added some random noise in here, but that should be kind of ballpark. Okay, so we have a random data set. The next thing that we need is we need a loss function to tell us for any choice of m and b, how far off are the predictions of our line from the actual target vector that we're trying to predict. So the function that we'll be using for our cost function is mean squared error. So we're going to take the difference between our target vector and the predictions from our line, we're going to square them, and then we're going to take the average of them. Okay, so the last part here is just our gradient descent loop. Okay, so we do have some hyperparameters to choose. We need to choose what value of h we're going to use. 1e to the negative 6 is, well, small enough. We also need to pick our learning rate. In this case, 0.05 is okay, but depending on your data, depending on what function you're doing gradient descent for, you may have to tune this parameter. You may have to try a couple different things and see what works. And then we need to choose how many iterations we want to run. And in this case, I'll do 100. It'll be super fast. So when we start this, we need some initial guess for what the slope and the intercept of our line of best fit should be. And to do this, I just sampled from a random normal distribution, so we just got kind of a random guess for both. Now, for each of these iterations, the loop is exactly what we've described previously. The first thing you have to do is you have to calculate your gradient of your cost function with respect to your slope and your intercept. Okay, so the way that you do that is, if you look here, for our gradient with respect to m, all right, is our cost function, or the mean squared error between our target vector and the predictions of our line given m plus h and b. All right, so just think about that for a second. The derivative of a function with respect to m means we don't have to care about the intercept, it's a constant. So here we have our cost function with respect to m plus h minus our cost function with respect to m divided by h. All right, so we just move m up just a little bit, see how that changes the cost function, and then divide it by the tiny little perturbation there, h. We play the same game for b, our intercept, except in this case we hold m constant. And now we have our mean squared error of b plus h minus our mean squared error of b divided by h. And then the way in which we update basically our predictions for m and b is we take our current value, subtract from it the gradient times our learning rate. Now when we run this code, right, everything ran successfully, and then we can plot our line of best fit here. And let me actually make this a little bit clearer. And maybe I'll make this one red instead of green. I think I like this better. Yeah, okay. So here now, this red line is our line of best fit that we just obtained through gradient descent. And so you'll remember to generate this data set, right, we used a line with a slope of 5 and an intercept of 13. And using gradient descent, we found that the slope for our line of best fit is about 5.22, or 5.23, I guess we could say. And then for the intercept, 13.26. Now, again, the slope and the intercept here are not going to be exactly what we use to generate the data because we added some random noise to it. So if we use like an ordinary least squares solver, like NumPy has polyfit, all right, this will evaluate some inputs and a target vector for a polynomial of any degree. In this case, our line is a polynomial of degree 1, right? So if we run this, what NumPy is saying is the line of best fit here has a slope of 5.2294 and an intercept of 13.2643. And that is very, very close to what we got through doing gradient descent. Okay, so this is as simple as it is. The main idea here, right, is in order to calculate your gradient, you don't actually need to do anything analytical, use any tricks of differentiation. All you have to do is just evaluate your function at 2 points very close together, and that's enough to differentiate it. One little technical detail to note at the end here is if the scale of our target vector y was much larger than this. Here it's between like -20 and 40, but if it was between, let's say, 0 and 10,000 or 10,000 and 20,000, okay, gradient descent would get a little bit unstable because in general, as the scale of your target vector increases, the value of your cost function tends to increase as well because your errors get bigger, okay? What that means is that your gradients get bigger, and they get so big that even for very small choices of h and very small choices of your learning rate, you end up taking massive steps that will completely miss your minimum. So in general, what you'll do is you'll normalize your target vector to be between 0 and 1 to keep gradients stable. Okay, it's just a numerical stability optimization. It's one of the reasons why, in general, inputs and outputs from neural networks are between 0 and 1. Okay. Anyway, that's just a little detail I wanted to point out here in case people try and run this and it breaks. That's one reason why it could. So anyway, that's it for this video. See ya.